Hi everyone, this is Kiranmay from H&S department. Today we are going to have a session on Compton effect and the problems regarding the Compton shift. So in this topic, we are going to discuss about state for the Compton effect, what is the Compton shift, and we will derive a formula for the Compton shift, special cases regarding the Compton shift, and some numericals based on Compton shift. So coming to the statement for the Compton effect. Compton effect, it is stated as when a monochromatic beam of high frequency radiation is scattered by a substance, the scattered radiation contains two components, one having wavelength greater than the incident called as modified component, another having the same frequency as the incident called as unmodified radiation. In this, you can see on the screen that there is one photon which got incident on a rest electron. Rest electron means which is stationary. When this photon is incident on this rest electron, the photon gets scattered with an angle phi, with a scattering angle phi, and the electron got scattered with a recoiling angle theta. So the and this is the unmodified photon which moves, which frequency does not change, and this is an modified radiation with changed wavelength, and the wavelength of modified radiation is greater than the wavelength of unmodified radiation. Now to derive Compton shift, let us consider an X-ray photon collide an electron which is at rest. So obviously the energy of the incident photon be h nu, and the momentum of the incident photon will be h nu by c. Energy divided by velocity will give you momentum. So let m naught be the rest mass of the electron. Then energy of the rest electron will be according to mass energy relation, Einstein mass energy relation. Energy is given by mc square. Since rest mass of electron is m naught, so the energy of rest electron is m naught c square. Since the electron is at rest, the momentum will be 0. Now before collision, the energy of the system will be summation of energy of incident photon and energy of rest electron, that is h nu plus m naught c square, and momentum of the system will be before collision will be h nu by c plus 0. This is the equations of the system before collision: energy h nu plus m naught c square and momentum h nu plus c by h nu by c plus 0. Now, when after the collision of photon with a rest electron, let photon be scattered with an angle of phi and electron be scattered with an angle theta. Therefore, phi is called scattering angle and theta is called as recoiling angle. Now, energy of the scattered photon will be equal to h nu prime. As we had taken incident photon as nu, here we had considered scattered photon as nu prime. Momentum of scattered photon will be equal to h nu prime by c. And energy of recoil electron will be, since the electron got scattered, its mass will be mc square, and momentum of the recoiling electron will be mass into velocity, that is m into v, where v is the velocity of the recoiling electron. So after collision, the energy of the system will be the summation of both photon and recoil electron. So h nu prime plus mc square, and momentum of the system will be equal to h nu prime by c plus mv. These are the equations for the energy of the system and momentum of the system after collision. Now let us apply conservation of energy, law of conservation of energy to the system, which states that energy neither be created nor be destroyed. So energy before collision is always equal to energy after collision. So from the before slides, you had two expressions for energy of the system. Before collision is h nu plus m naught c square, and energy of the system after collision is h nu prime plus mc square. So substituting these two equations in the law of conservation of energy, we get h nu plus m naught c square is equal to h nu prime plus mc square. Now just take mc square onto the one side and take h nu prime onto the other side. You'll get mc square is equal to h nu minus h nu prime plus m naught c square. So from the first two terms, if you take h as a common, h into nu minus nu prime plus m naught c square. Now squaring on both sides will give you m square c power 4, and other side it will be like a plus b whole square formula. Just apply the formula a square plus b square plus 2ab. So it'll result with an expression m square c power 4 is equal to h square nu minus nu prime whole square m naught square c power 4 2h nu minus nu prime into m naught c square. Now just apply nu minus nu prime whole square as a minus b whole square formula and rearrange the terms. You'll get a formula for m square c power 4. This is the final expression what we get by applying law of conservation of energy. Now in the next step, we are going to apply law of conservation of momentum, but in two directions. One in the along the incident radiation and another perpendicular to the incident radiation. Since along the incident radiation, as it is a horizontal component, we are going to take the help of cos angles, and in perpendicular to the incident radiation, in the vertical direction, we are going to take the help of sine angles. So coming to the conservation of momentum, so the same statement, momentum before collision is equal to momentum after collision. As we are taking in horizontal direction with cos function, we are supposed to take. So in the before slides, you can observe the expression for momentum of system before collision as h nu by c, and after collision as h nu prime by c plus mv. So using these two expressions, h nu by c before collision is equal to h nu prime by c cos phi. Why phi? Phi is the scattering angle of radiation. So h nu prime by c is the radiation photons momentum. So h nu prime by c into cos phi plus mv into cos theta. Theta is recoil angle of electron. So mv into cos theta. So just get h nu times terms onto the one side. You'll get mvc cos theta is equal to h nu minus h nu prime by h nu prime cos phi. Now squaring on both sides, you'll get one expression in terms of m square v square c square cos square theta is equal to h square nu square plus h square nu prime square cos square phi minus 2h square nu prime cos phi. Now coming to the other direction, that is vertical direction, here we are going to take the sine angles. In vertical direction, there is since the photon is coming only in the horizontal direction, there is no vertical component before collision. So vertical component before collision will be equal to 0. That is equal to momentum in vertical direction after collision, that is equal to h nu prime by c sine phi plus mv sine theta. So h nu prime by c, just get the terms onto the other side of the equation. So by rearranging and squaring on both sides, you get m square v square c square sine square theta is equal to h square nu prime square sine square phi. These are the two expressions, one along the incident radiation and another along the perpendicular direction of incident radiation, that is horizontal component and vertical component. Now adding about two expressions, one along the horizontal direction, another along the vertical direction, just add them together, you'll get like if you take the common of m square v square c square on left hand side, you'll get cos square theta plus sine square theta, which is equal to 1. So left off with m square v square c square. On the other side, the terms will get cancelled up and you are left with h square nu square plus h square nu prime square minus 2h square nu prime cos phi. This is the final expression for final expression from law of conservation of momentum. There is another expression what we had derived earlier, that is this is the equation from law of conservation of energy. Now using these two final expressions, just subtract equation 2 from equation 1, you'll get m square c square into c square minus v square is equal to m naught square c power 4 plus 2h into nu minus nu prime m naught c square minus 2h square nu prime into 1 minus cos phi. Now to have all the terms into the mass, rest mass of electron, just using special theory of relativity, we are going to change mass in terms into mass into in terms of rest mass of electron. So m is equal to m naught by root over 1 minus v square by c square. This is from special theory of relativity. Now just square on both sides, you'll get m square is equal to m naught square by 1 minus v square by c square. Just rearranging the terms, you'll get m square c square minus v square is equal to m naught square c square. So in place of m square c square minus v square, we are just going to replace this expression. We will get m naught square c square into c square is equal to m naught square c power 4 plus 2h nu minus nu prime m naught c square minus 2h square nu prime into 1 minus cos phi. Now just see the terms. First term of this expression will get cancelled with the left hand side term. So by cancelling them, you are left with two more terms on the right hand side. That is 2h into nu minus nu prime m naught c square minus 2h square nu prime into 1 minus cos phi. Just get the terms onto the one other side, rearrange the terms, you'll get c by 1 by nu prime minus 1 by nu is equal to h by m naught c square into 1 minus cos phi. Now from this right hand side term, if you observe, the denominator is having c square. Now get 1c from this denominator onto the other side, left hand side. Then it will be rearranged as c by nu prime minus c by nu is equal to h by m naught c into 1 minus cos phi. C by nu prime is nothing but lambda wavelength. So lambda prime minus lambda is equal to this one. So lambda prime is equal to lambda plus h by m naught c 1 minus cos phi. So which means that the scattered wavelength is equal to summation of incident wavelength plus one more term, which says that the wavelength of scattered radiation is greater than the incident radiation. Therefore, Compton shift can be given as d lambda, that is lambda prime minus lambda scattered radiation, wavelength of scattered radiation minus wavelength of incident radiation, that is given by h by m naught c into 1 minus cos phi. This d lambda is nothing but Compton shift. Now from this we can arrive with the special cases by putting different angles for the scattering angle phi. If phi equal to 0, cos 0 will be equal to 1. 1 minus 1 will give you 0. So there is no Compton shift in case if the scattering angle is 0. If the scattering angle is 90 degrees, cos 90 will be 0. So the value will be h by m naught c. If the scattering angle is 180 degrees, then cos 180 will be minus 1. So 1 minus of minus 1 will give you 2h by m naught c. This is the three different special cases for the Compton shift. Now we can see some more numericals problems dependent on this Compton shift formula. One of them is on the screen, you can observe that they had given the incident photon wavelength, that is lambda value, and they were asking you to find out the scattered radiation wavelength, that is lambda prime, and they had given the scattering angle also, that is 45 degrees. So the given things are incident wavelength, that is lambda 0.5 nanometers. Since it is in nanometers, we have to convert that into meters, 0.5 into 10 power minus 9 meters. And they had given scattering angle, that is 45. So phi is equal to 45. Now substituting that in the formula, lambda prime is equal to lambda plus h by m naught c into 1 minus cos phi. So lambda they had given you, substituted, plus h is Planck's constant, as we know that 6.6 in 10 power minus 34. M naught is rest mass of electron, that is 9.1 into 10 power minus 31. C is velocity of light, that is 3 into 10 power 8 into 1 minus cos phi. Phi is 45 degrees they had given you. Substituting them and calculating, you'll arrive at 0.5007 into 10 power minus 9 meters. This 10 power minus 9 meters, we can take it as nanometer. So the final answer for the scattering wavelength, scattered radiation wavelength, is 0.5007 nanometers. Let us see one more numerical. With the same question, there is a small change of values. That is, they had given the incident wavelength as 3 angstroms and the scattering angle is 60 degrees. So they were asking you to find out, there's a small mistake over here. This is phi equal to 60 degrees. Okay. They were asking you to find out the wavelength of scattered radiation. The same thing you can do. Armstrongs, you can convert into meters by taking the conversion. 1 Armstrong equal to 10 power minus 10 meters. Just substitute the values in the formula. By doing mathematical calculations, you'll reach at the value of 3.01212 Armstrongs. Let us see one more numerical. In this one, they had a question that in Compton scattering, the incident photon wavelength is doubled when it is scattered through an angle of 90 degrees by the target material, which means that if the incident wavelength is lambda, then the scattered wavelength will become double. That means 2 lambda. And the scattering angle is 90 degrees. Again, they were asking you to find out incident wavelength. So that let us substitute that lambda prime is equal to 2 lambda, that is double of incident radiation, and phi equal to 90 degrees. Just substituting them, rearranging them, we'll get 2 lambda is equal to lambda plus h by m naught c into 1 minus cos 90. If you get lambda from right hand side to left hand side, 2 lambda minus lambda will become lambda, h by m naught c into 1 minus cos 90 is 0. So left off with lambda is equal to h by m naught c. Lambda is equal to h value is 6.6 into 10 power minus 34. M naught, rest mass of electron, is 9.1 into 10 power minus 31, and the velocity of light 3 into 10 power, right? Just substituting those values in the formula and making the mathematical calculations, you'll arrive at 0.244 angstroms. Thank you.